5, you have a situation where you have 3 blocks on a surface.
Oh, you're giving you this one.
Yeah, and it does give you the frictional coefficient.
What is it called again?
Mu. All right, so we've got some surface. In mine, the coefficient of friction was 0.4 or 0.14. Okay, and then you have 3 blocks, and those all have different masses. So I kind of did this to the side. I said the mass of block 1 is 2 kilograms. The mass of block 2 is, in mine, 1.8 kilograms. And the mass of block 3 is 6.4. Yeah, all our numbers are going to be different, but the process should be the same. Okay, the question in this problem is, what is the force of block, what is it? Forgot. Block 2 on 3 or block 3 on 2? Block 2 on 3. That's what it's saying. What is the force of 2 on 3? That's what we're trying to, 2 on 3. That's what we're trying to solve for. Force of block 2 on 3. Okay, it gives you one other thing. It says that there is some applied force equal to 100 newtons. So somebody's behind all of these blocks and they're pushing it from behind with a force of 100 newtons. And they're not pushing each one individually, they're pushing all of them. Yeah. Okay, so we know this is going to be a Newton's second law equation. So writing this, although it's not much, is a start. And the net force is going to be equal to mass times acceleration. The first assumption that you need to make is that we can combine all these 3 blocks into 1 block in our problem, right? Since that applied force is going to be felt by all of them in some way, we can combine all of their masses, right? Since they're touching and pushing each other. So what you would do here.
So why can't we combine all the masses if they all have different
No, they all have the same coefficient of friction.
Well, they have different masses.
They have different masses, so their force of friction is going to be different. Yeah. But to simplify the system, we can add all those masses together and just treat it as 1 block because they are moving as one. They're not moving separately. Okay, so what I did is, right, this is my representation of combining the 3 blocks and doing a free body diagram of that. So on these 3 blocks, we basically have 2 forces. We have 100 Newton applied force to the right, and then what do we have to the left?
Same.
No. Friction. Okay, because we're given this frictional coefficient up here. So we're pushing it to the right, friction's opposing us to the left. Right? By combining them, what we can do is we can solve for the net acceleration that each block's going to fill. Like I said, they're going to move as 1 unit, so they're all going to accelerate at the same value. Right? So in order to do this, what is net, based on a free body diagram, what is the net force equal to? 100 minus what? The frictional force, right?
Where did we get 100 from?
From the applied force in the problem, it says the blocks are pushed with a 100 Newton force. Or it's in the picture or something, I don't know. So the net force, from this drawing, what you can say is the net force is 100 newtons minus our frictional force. Careful. Right? Minus our frictional force, that will be equal to MA. M being the mass of all the blocks. Right? Because we're simplifying it a little bit. So this would be all of the blocks right here, not just one mass. Yeah, 100 minus the force of friction. Net force, right minus left in this case. Okay, so kind of plugging in what we know, this is what we get. We have 100 newtons, okay, minus, for frictional forces, remember it's a percentage of the weight, so mgu, right? But since we are combining all the masses, it's going to look like this. M1 plus M2 plus M3, right? Times G, not Q, G mu. Right, that's the left, that's the left side. Applied force minus our frictional force. On the right side, the only thing that we need to do is this, M1 plus M2 plus M3 times A. You just combining all the masses
So
together.
what, why M is equal to the, what's the friction? Cause in the
M?
first equation, that's what you put right there. The force- Oh, mg the thingy, never mind,
Yeah,
I got on
mu.
the same page.
Yeah,
Sorry.
mu.
Oh.
Okay, so looking at this equation, we can solve for the acceleration that all the blocks feel, the common acceleration they have, by dividing through by this, all of our masses. No. No, it's moving in the x direction.
Could you replace the
So that's
mu
acceleration
with
x.
the,
Gravity's one.
Yeah.
could you replace mu with the 0.4?
Yeah. I'm just doing some rearranging first because you're going to see something simplify. So when I divide through by all three masses, what you're going to notice is that this mass over here cancels out. And what we have is 100 newtons over our three masses. Okay. Minus, don't forget about this, G mu is equal to A.
But are they
G is 9.8.
Have they just canceled out M1, M2, M3?
I did over here, but this is these two terms. These are two terms right here. So I have to divide both by that. That's where I get 100 over. You look
Oh,
lost.
because minus.
Yeah, because of that minus. Two terms. Okay, so to find acceleration, this is what you would do. When I plugged in my numbers for my problem, I got this. Okay, the reason that we need to solve for the acceleration is because although the 100 Newton force is being applied to all of the blocks, they're all going to feel a different portion of that 100 newtons, and it's not going to be equal between all three of them because they have different masses. So the force of friction on each one is going to be a little bit different. And also in your picture, you'll see that like block 1 is pushing 2 and 3, block 2 is only pushing 3, block 3 isn't pushing anything.
They're at negative. Oh, I read the 6.
I got 2.691. Is that right?
No, A is not the answer. This is just the first step. Okay. Because we, like I said, we need to find the acceleration so we can look at each block individually. Otherwise, we can't go
Where
anywhere.
G is gravity. 9.8.
Yeah. Okay, so my point here is, when you look at your drawing, pretend all these blocks are touching. Okay, each block is going to feel a different portion of this force because block 1, the friction from 2 and 3 is going to oppose some of that applied force. Right? So if you want to think about it this way, block 1 is pushing 2 and 3 as well as itself. Right? So it's not going to feel that much force. Block 2 is pushing 3. And then block 3 is not pushing anything. And so that 100 newtons for block 3 is going to act a little bit differently. The problem says, what is the force of block 2 on 3? Right? No. Yes? Or is it block 3 on 2? No, it's 3 on 2. I wrote it wrong the first time. Okay, but here's the thing. Does that matter? Why not? Which law says it doesn't matter? Okay, so if it asks for the force of block 3 on 2, we know that that also has to equal the force of block 2 on 3. They have to be the same. Newton's third law. Okay, if 3 pushes 2, then 2 pushes 3 backwards. So this helps us in our problem solving because what we can do is we can look at block 3 only. We can look at a free body diagram of block 3 to look for the force of 2 on 3. Remember, for free body diagrams, it's only the forces acting on that body. Okay, so if we solve for this, really what we're solving is for the answer. Okay. So the next step would be, after you find acceleration, is to draw a free body diagram of block number 3. So we're going to look at the force of block 2 on 3 is what we want to solve for. Okay, so free body diagram of block number 3 would look like this. You've got force of gravity, normal force. Do these matter in this problem? No, because they're not accelerating up or down. Right, but those do exist. They'd probably be worth your time to draw them in at this point. Okay, we've got, going to the left, what do we have?
Force is 3, 1, 2.
No, that would be on 2's free body diagram.
Force on 2.
No, 3 to 2.
Because you said 3 on 2. Yeah, remember this is a big point with free body
Oh,
diagrams.
on-
We only want the forces on 3. So yeah, block number 3 is going to push block number 2, but that's 3 on 2. That's on a completely different free body diagram.
2 on
No, that's
No,
not.
2
Well,
on,
2 on
okay,
three
well
goes
let,
right
yeah,
direction.
okay, so we can do 2 on 3.
3. So that'd be friction.
This would be the force of block 2 on 3, right? That's going to be what's pushing it forward, is the block 2 actually pushing it. So what was this?
friction.
This is friction.
Wait, but isn't 3 also pushing on 2? That's the opposite.
Right,
Oh,
but
yeah.
like I'm trying to get you, you're saying 3 on 2.
But every-
On 2 is on some other free body diagram for block 2.
Oh.
That's a completely different picture.
You also drew down 1 was on 3.
Yeah, one would act on 3.
But is that the same thing as 2 and 3? Or that,
Well, we're going to look at the 3 blocks individually right now. Okay. What we could do is say 1 pushes block 2 and 3 and add their masses together. If we wanted to do that, but we're not going to do that. We're just looking at 3. Okay, so this is my free body diagram. From a free body diagram, usually what you do is this equation, F net is equal to MA. Right? That's usually what you do. Since we're only looking at block 3, this is going to be mass 3. The acceleration is the same for all 3 blocks, so we don't have to worry about labeling that. So looking at our free body diagram, what is F net equal to? These are the same, so they don't come into play.
oh.
It's stronger to the right, right? Okay, so since it's stronger to the right, I'm going to write this force first. Force of 2 on 3 minus
Oh, friction.
force of friction is equal to M3A. And so now we've got our equation to use. Basically what this is saying is block 2 is pushing block 3 harder than that 100 Newton force. But some of it's being taken away by friction. Right? And so that's where we're going to get the actual force on block 3 from. Okay, so here, now all we're doing is basically putting in what we know. Okay, so for the force of 2 on 3, what am I going to simplify that to? Well, every force is some mass times some acceleration. So what mass would I put here?
2 mass.
This is, since our free body diagram is for block 3,
So put-
we're going to put, this is mass 3. Okay, so it would be M3 times A, I believe. Hold on. No, wait, before we do this, let's do this, because this is going to make our lives easier. We're trying to solve for this. Yeah. So let's rearrange before we do that. Okay, we're trying to solve for this. Sorry. See, I got confused there. And I would have started plugging in numbers that wouldn't work. So, the force of 2 on 3 is equal to M3A plus the force of friction. Which, if you didn't draw a free body diagram and I wrote this, you'd probably say, well, shouldn't it be minus the force of friction because it's going in the opposite direction? But from the free body diagram, you can tell that the net force has to be an addition. Okay. So here you just plug in numbers. Mass of block 3 in my problem was 6.4. Then the acceleration we solved for was 8.432. Okay. Over here, this is a frictional force. So yeah, you're going to do M. All right, this is still block 3, so it's going to be, in my problem, is 6.4. Well, that's given. Mass number 3. 6.4 times 9.8 times your coefficient of friction, which in my problem was 0.14. Once you solve that statement down, you'll get the answer of force 2 on 3 and also the force of block 3 on 2.
Oh, wait, what's that 8.43?
That's the acceleration we solved for.
Yeah. Mine was 3.05.
Well, yeah, whatever you got in the first part.
Can you run through all those numbers again? So 6.4 is block 3.
Let me do this.
What's wrong?
No, it's all right. No, I just want to, I'll write this using variables so you're not confused. So this is the mass of block 3 times the acceleration you found in part 1 plus Force of friction is m, in this case it's number 3, so we're looking at block 3, mg, and then your mu. That's where I got all those numbers from. So you just have, basically all you have to do is just plug in the numbers that you solve for acceleration, and then the mass is given, g is 9.8, and then the coefficient of friction is given as well.
Acceleration is not gravity. Is the acceleration gravity?
No, not that one.
Okay.
No, because that's not friction.